And maybe I'll start.
Yep. Okay, so it's my pleasure to introduce Simone Pigolotti from WOST. He's the first speaker of today's tutorial session. His talk title is Introduction to Stochastic Thermodynamics. Okay.
Can you hear me? Yes.
Yes.
So first of all, I would like to warmly thank the organizer for the honor of giving me the opportunity of opening this workshop that looks really interesting. So as we were discussing with Takahiro, I suspected that one of the reasons for this invitation was this effort that Luca Peliti and I made in the recent years of writing an introductory book on stochastic thermodynamics. So the idea of this book was really to somehow try to explain stochastic thermodynamics in the way I wish I had learned it. So at some point while I was learning stochastic thermodynamics, I felt that perhaps I needed to, it would have been easier for me to learn it if the arguments were presented in a certain way. And that was pretty much the rationale behind this book. So we hope that this book will help people that approach this field in learning without too much effort. But of course, this is a book, so this is not something that one can present in a 1-hour tutorial. So when I received this invitation, I started scratching my head and think about how do I really strip this material to the bare bone and essentially give you in 1 hour the main take-home points, what I believe to be the most like basic substantial points of stochastic thermodynamics. And after thinking about it, I reached the conclusion that, at least in my opinion, there are two concepts that really lie at the core of stochastic thermodynamics. The first is that you can do some sort of thermodynamic bookkeeping for stochastic physical systems, meaning that you can identify for a stochastic system work, heat, and energy, for example, and you can do this in a stochastic way, so at the level of individual trajectories. And the second crucial concept is that there is a relation between entropy production and something that I would call statistical irreversibility, and I will later explain what this is. And this lies at the core of the so-called fluctuation relations that are among the most important results in stochastic thermodynamics. So I don't know about you, but if you are in my same time zone, it's evening, and I will do my best to avoid this phenomenon. So what I would suggest is that since I have essentially two topics in my tutorial, I would like to split this in two parts that will be roughly half an hour each. Perhaps the first is slightly longer than the second. And consequently, there will be half an hour discussion, but we can split it in two parts. So we'll have 15 minutes after the first block and 15 minutes after the second block. So I think one interval in the middle might make this a bit lighter. Is that okay? I hope that's fine. So at some point I will stop and I will take questions, and we can start following the procedure that Takahiro illustrated. Okay. By the way, do you see my pointer?
Yes.
Yes.
Oh, okay. Great. Thank you. Yeah. Okay. So let's talk about thermodynamic bookkeeping. So I'd like to introduce this with this image. This is a portrait of Luca Pacioli. Luca Pacioli was a monk in the Renaissance. He was born in San Sepolcro, which is a small town in Tuscany that happens to be very close to where my family is from. And I'm showing you this painting because this guy is widely regarded to be the father of accounting and bookkeeping. So he is one of the people that he was not really the first inventor, but he is regarded as being the person that formalized the so-called double entry system. So this is perhaps one of the most used system in it lies at the core of modern bookkeeping. And the idea is that if you have an economic transaction, the best way to record it is to do it twice. So you would record it once as a credit and once as a debit. So if I give some money to Takahiro, in my book there will be an entry Simone Pigolotti gives some money to Takahiro Sagawa, and Takahiro Sagawa receives some money from Simone Pigolotti. So this is a good system because essentially, since all debits should match all the credits, it basically avoids mistakes. So we will essentially follow this idea in trying to understand bookkeeping for thermodynamic systems. And now let's start talking about thermodynamic itself. So I want to introduce the setup that I will focus on for my entire tutorial. So the idea is that we have a system that is a small physical system. And to keep things simple, we imagine that the system has discrete states and is Markovian. So again, this is not a requirement. There is discrete states. We could have continuous states, but then we would have additional complication related essentially to stochastic calculus. But the basic physics would be the same. There is a technical requirement. There is the states should be invariant under time reversal. So we don't want to consider, for example, underdamped system where momentum will change sign at the time reversal, or system subject to magnetic fields, spins, things like that. So again, this is a technicality, and we will see later why this is important. So the system, if it was left to itself, we would imagine that it would, let's say, be some sort of equilibrium state. But there are two kinds of, the system will interact with two external things. One is a thermal reservoir, a heat reservoir at a fixed temperature T, and this is essentially the source of stochasticity. This is why the transitions between these states are stochastic. And then there is an external agent that can exchange work with the system. And in particular, our assumption is that there are two different non-mutually exclusive ways in which this agent can interact with the system. One is by altering its energy, so by changing the energy of each of the system state over time. And the second is by providing energy when certain transitions occur. So in the first case, I will talk about manipulation to keep things, give it a name to this process. And in the second, I will talk about driving. And this is often a way we model, for example, biochemical systems where the system represents systems of chemical reaction, and the driving represents the fact that certain reactions are driven by consumption of ATP, for example. So this is the setup. So because of, we say that the system is Markovian, so it will obey a master equation that I will write in this form. So Kx x prime is the rate of jumping from state x prime to Kx. This in principle can be time dependent. The expression of these rates depend on what the system actually is and on our physical assumptions. And at some point during this tutorial, we'll see how it depends on the physics of the problem. So because the system is described by a master equation, it's useful to think how a trajectory of the system will look like. So the system will spend some time, exponentially distributed time, if the rates are constant in each of it, in one of its state, and then there will be a sudden jump to another state and so on. So trajectories of master equations typically look like this. So we'll call dwells the times spent in each state, and jumps these instantaneous transitions. So to start thinking about the thermodynamics, we should think that the action of the thermal reservoir is really responsible for these jumps. So the jumps is where essentially the thermal reservoir is providing energy to the system. And we saw that according to our assumption, the external agent can contribute as well with this contribution that we call driving, so by providing energy during these transitions. And during dwells, the system is in a single state, so the thermal reservoir is not exchanging energy with the system, but there can be exchanges with the external agent if the external agent is manipulating the energy of the system. So this can happen also outside jumps. So this is a first somehow summary of the kind of energy exchanges that can happen during a trajectory. And now we'll dissect them and quantify them. So we start by talking about the system energy. So the idea is that at each given time, each state of the system is characterized by a certain energy. So you can imagine these as really as functions of time. And again, this can be time dependent because the external agent can alter the energy of each of the states. And so there will be one function per state. And so we can define a stochastic energy, which is simply the energy computed on the trajectory. So by replacing this dependence on the state by the state that the system actually occupies at time t. So in this illustration, if the system initially is in state 2 and then it jumps to state 0 and then it goes to state 3, then the stochastic energy will be the function denoted by this bold line. So it will be a discontinuous function of time. This is quite, I would say, it's quite straightforward. Now we can talk about stochastic work, and here, as we already discussed, there will be two terms. So there will be work done when the agent is manipulating the system, and work due by driving. And as we said, depending on the model and the system we are considering, we can have only one of these two terms or both in general. So the manipulated work is simply in each of these intervals in which the system remains in the same state is the integral of the energy changes. So if the energy of the system change is because this energy must be provided by the external agent according to our assumptions. And to this contribution, we will add another contribution, which is this contribution from driving. So we call delta xk xi the work that the external agent provides when there is a transition from y to x. And of course, we have to sum all this contribution to calculate the total work performed by the external agent over a certain time interval. So implicitly, I'm adopting the convention, which is used quite common in stochastic thermodynamics, that work is positive if it's done on the system, and it's negative if it's received by the agent. At this point, we can immediately define the stochastic heat. The stochastic heat is simply the sum of the energy provided by the reservoir at its jump. And this is the idea, is that every time there is a jump, the system, the energy of the system changes by a certain amount. The external agent might provide a driving, so an energy contribution, and the rest must be provided by the heat reservoir because the energy must be conserved. So if I according to this consideration, I can write the total stochastic heat in a given trajectory as a sum of terms, one for each jump, and each term will have this form. So as I said, there will be one contribution due to the energy difference and another contribution due to the driving. So it's just this energy balance in each jump. And here the convention is that if Q is equal to 0, then it's released by the system, and negative is absorbed by the system. Okay, so now armed with these definitions or the identifications of thermodynamic quantities, we can move to the first law of stochastic thermodynamics. So if I look at the difference between work and heat, according to our definition, you can see that if I integrate these terms, I will get essentially energy differences. I will get the energy difference at before and after each transition. So this term will cancel out with these terms, and this term will cancel out with this term. So I will remain with essentially the energy difference between the last and the first state. And so I get essentially the first law of thermodynamics, that energy is conserved along transformation. So summarizing this initial part of my tutorial, we derived, or better we can say defined according to quite simple energy considerations, some mathematical expression for the stochastic heat, work, and energy for a single trajectory of a master equation. And we have shown that these expressions formally satisfy the first law of thermodynamics. That is a way of stating that the energy balance is always satisfied. So I would say that Luca Pacioli would be proud of us, because essentially we did exactly the same as what one does in bookkeeping. We register these energy exchanges as in both in several of these quantities, and we saw that in the end all these exchanges have balanced out, so our calculation is correct. Good. So now we took care of the energy balance, and we move to entropy balance, which is slightly more tricky. So in this case, we will also proceed in analogy with the traditional thermodynamics, but as usual, we have to be careful because we want to define entropy at the level of individual trajectory, not as an average quantity. But again, in analogy with traditional thermodynamics, we can say that the total entropy produced by the system at the level of the individual trajectory will include two contributions. One is the change in entropy of the system between the final and the initial time. And then there will be a second contribution, which is the entropy released into the reservoir. And again, now we need to define these quantities at the level of individual trajectories. Let's start with the system entropy. Here, the idea is to define it according to this formula. So we say that the system entropy is equal to minus Kb times the logarithm of the probability of being in a certain state at time t. And this definition is chosen such that if I average this quantity, I will get the traditional Gibbs von Neumann entropy. So the idea that the entropy is minus Kb sum of Px log Px. So this is just chosen in analogy with the traditional equilibrium statistical mechanics. For the reservoir entropy, again, we can proceed in parallel with the traditional thermodynamics and say that since the reservoir is assumed to be large and always at equilibrium at a temperature T, and given that we already defined stochastic heat, we can just assume that the entropy released into the reservoir is given by the same expression as in traditional thermodynamics. So this will be the heat released divided the temperature. The only difference is that in this case, the definition of the heat is the stochastic heat that we introduced before. So if I sum these two contributions, I will obtain the total entropy produced during the process. So I will have one term again, which is the difference in systems entropy that I can write in a compact form this way. And then I can use my definition of stochastic heat to express explicitly this in the reservoir entropy. So if we look at this expression, it doesn't really say much at first sight. So we should, in the following, try to essentially make sense of it and understand what does it tell us about the physics, and in particularly about irreversibility of an non-equilibrium process. Okay, so the first thing I would like to discuss at this point is to make a step back. If you remember at the beginning, I said that we should think about how the rates of the master equation are related with thermodynamic quantities, because we have to relate the stochastic dynamics with these thermodynamic exchanges. We start this discussion with a simple case, which is the case in which the system is at thermodynamic equilibrium. In this case, given our assumption, we know that rates must satisfy the detailed balance condition, meaning that the ratio of a forward and a backward rate among each pair of state must be equal to the exponential of the energy difference between these two states divided by kBt. And this condition, I will not discuss it at length, but essentially guarantees two facts. One is that if the system is let to evolve by itself without any action of the external agent, then the distribution over states will relax to the Maxwell-Boltzmann distribution. So as we say, the system will go to the equilibrium state, and this state is stable, dynamically stable. And the second outcome is that currents vanish in this equilibrium state. So I can define currents associated to any pairs of states in the master equation, and you can easily see that if rates satisfy this condition, then all these currents are identically zero. So I introduced this detailed balance condition because one important concept, one important idea of stochastic thermodynamics is that a very similar condition holds for non-equilibrium processes. So this is sometimes called the generalized detailed balance condition. It has different names sometimes in different references. But essentially, the idea is that from the point of view of the thermal reservoir, there's no distinction between an equilibrium and a non-equilibrium system. So if you think about, for example, the effect of manipulation, since the manipulation is a slow process and the interaction with the thermal reservoir is an instantaneous process, the reservoir cannot possibly know whether the system is being manipulated and therefore out of equilibrium or not. For this reason, we should expect that a condition analogous to the detail balance condition will be valid also for our non-equilibrium case. So the only difference between the generalized detail balance condition and the traditional detail balance condition is that now energies are allowed to depend on time, and I added to the energies the contribution of the possible contribution of external driving. And one way of writing this equation in a possibly more suggestive way is to say that the ratio of these two rates must be equal to the exponential of the heat provided by the reservoir in this transition divided KBT. And this stress that essentially the reservoir only cares about how much heat is providing during a certain transition and not whether the system is in equilibrium or not. This is kind of a subtle point of stochastic thermodynamics, and it's quite hard to summarize in one slide. I hope the argument was convincing. Okay, so we needed this assumption because using this assumption, we can now say something more about the average entropy production rate. And the way to do that is to look at the entropy change during a jump and during a dwell, so during times in which the state the system does not vary. So if the system is during a jump, we know that the reservoir entropy changes by an amount which is the heat released in that transition over T, which is this expression if we use generalized detail balance. And there is a change of system entropy, which is simply Kb times the logarithm of the ratio of the probabilities, as we saw before. In contrast, the rate of entropy change during a dwell, if I write it in a differential form, it will be, since we know that the reservoir is not participating, there is only a contribution due to change in system entropy, and simply I have to derive the logarithm of P. And if I write, if I use the chain rule, I can express this change in this form. And if I average this term, you can see that the average of this term is 0 because of conservation of probability. So the average rate of entropy change during a dwell is 0, and there might be an average contribution only during jumps. This is what we learned from this calculation. So now I can use, if I want to average this contribution, I can use the fact that jumps occur at an average net rate, so sum of a rate of jumping in one direction minus rate of jumping in the other direction, average, which is given by the current between the pair of state. And so if I want the total average entropy change, rate of entropy change, I need to take this quantity, multiply it by the corresponding current, and average overall possible jumps. And this gives the celebrated Schnackenberg formula, which is expressed in this box. And I have a factor 2 at the denominator just because I don't need to count each pair of states twice, one for x prime and the other for x prime x. So if you substitute the expression of the current, you will see that the logarithmic term has always the same sign of the current. So if this term is larger than this term, then the logarithm is positive, otherwise it's negative. So each term in this sum is non-negative and vanishes only if the current vanishes, which means that the entropy production is, the average entropy production rate is always non-negative and vanishes only if all the currents vanish, which is the condition of detail balance, which is the condition of thermodynamic equilibrium. So this is a reinsuring. So we discovered that our definition of the entropy production is consistent, at least on average, with the second law of thermodynamics. So the average entropy production rate cannot be negative. So this is summarizing what I just said. So this term is just, each term of this sum is always negative, expressed in this form, and vanish only, the whole sum vanish only at the detail balance condition. And again, second law of thermodynamics is valid only on average. And of course, the question here is, well, but now what about individual trajectories? Can entropy production can be negative for individual trajectories? I think this concludes the first part, I think, and I'm happy to take questions at this point. Okay, then let's move on, and we'll the second part of my tutorial will be a little bit more technical out of necessity. But first, before we start, I would like to give you somehow a bird's eye view of what I would like to show you. So the idea, the target of the second part of my tutorial is to introduce and actually prove fluctuation relations. So these relations are important constraints on the statistics of the entropy production. In particular, will help us understanding the question that I laid at the end of the first part. So what happens to, what can we say about entropy production for individual trajectories? It's quite easy to derive, it's actually very easy to derive fluctuation relations if we first make a connection between the stochastic entropy production that we introduced in the first part of my tutorial with something that I will call statistical irreversibility. And as I mentioned in the beginning, I will tell you more precisely what this is. So we need to essentially first establish this connection. But before we do that, we first need to talk about something that in physics is called path probabilities, which is probabilities of entire trajectory of a given stochastic process. In this case, we are talking about master equation. So this part will be a little bit more technical. I will try to make it as light as possible, omitting some details. I hope I will give you the idea of how this works. So unfortunately, I will have to start from this last part, which is might be a slightly dry, but again, I will present it in a hopefully quick and painless way. So the idea is that, again, we have a trajectory of our master equation, and we want to compute the probability density of that particular trajectory. And the reason for that will be clear in a few slides. So what we start, our first tool to achieve this goal is the infinitesimal propagator, which is essentially the probability that the system is in a certain state after a small time interval, given that it was in another state before this infinitesimal time step. So this propagator will involve, from the master equation directly, involves a delta function. So most likely the system will stay in the state where it was because the time step is small, and then there will be a first order correction. And this matrix contains the off-diagonal matrix. The off-diagonal elements are nothing but the transition probabilities. So that's, of course, the probability of leaving the state in a time dt. And off-diagonal, you have minus the sum of the out rate of state I. So I think, yeah, this should be k out x, k y x. Sorry, the notation is not consistent. So this would be ki actually. And this is because essentially the probability of remaining in the same state in a time dt is 1 minus the sum of the out rates time dt. So with this propagator, we can essentially slice down our total time interval in infinitesimal time interval and say that the probability of the whole trajectory is to the leading order the probability of the first state, which is P of x0 times t0, times the probability of the second state, which in this case is the same because there's no transition here after an infinitesimal time step, and then the probability of remaining again in the same state and so on, and then there will be a transition in this particular interval and so on and so forth. So essentially I will have to multiply these small propagators for all the infinitesimal time intervals that make up my my total time interval. Good. To simplify this expression, we can collect together all the terms inside each dual, so inside each of these intervals in which the system state does not change. So we saw that in this case we have that the propagator is 1 minus the total out rate of a given state times dt. And when I make this product, I can transform it into the exponential of the sum, and therefore I can, in the limit of a small dt, I can write it this sum as an integral. So this is nothing but the exponential of minus the integral in the dual during the dwell time of the out rate from the state. So doing this for all the duals, I will obtain that the probability of the entire trajectory is the probability of the initial state times the probability of all the rest given the initial state, and all the rest will contain terms corresponding to duals, which are this exponential of an integral, and terms corresponding to jumps, which are simply the rate, the jumping rate at the time of the jump, multiplying by dt. And all this dt I'm omitting in this expression. So this is a slightly ugly expression, but it will be useful for what follows. So this is a summary, and one can show that this probability is actually normalized. And just to make this expression, so this essentially will mean that the sum over all possible trajectories weighted with their probability is equal to 1. And just to make things more explicit, this notation, normally we mean a very high dimensional state, space of trajectory, but in this case, it's something we can write explicitly because we can somehow enumerate trajectories, so to say, by first summing over all possible number of transitions that might occur during the chosen time interval from 0 to infinity, then summing over all possible states visited by the trajectory in order, and then integrating over the time at which each of these jumps has occurred. And now you see why I didn't include the dt of each jump here, because I'm having it in the, I'm essentially absorbing it in the differential. So this is our notation, and this essentially is a tool that we will use for what follows. So now we can use this tool to talk about what I was mentioning at the beginning, which is the concept of statistical irreversibility. And before we do the math, let's talk about what this means. So the idea is that at equilibrium, you can show using these formulas that one peculiar feature of equilibrium is that the probability of each trajectory is the same of its time reversed. So there's no asymmetry, there's no temporal asymmetry in the equilibrium state. And also intuitively, we associate the fact that a thermodynamic system is out of equilibrium with the fact that the dynamics is irreversible. And we want to quantify this irreversibility by essentially looking at, if you look at, say, typical trajectories of the process, how large is their probability compared with their reverse trajectory. So a trajectory will start from the final state and go back to the initial state. This is essentially the idea that we have in mind. So to formalize this concept of reverse trajectory, we have to do a few things. So the first thing is, so far we have described the manipulation with the time dependence of the energy, but now it's convenient to do it with a certain function lambda. So now instead of having energies that depend directly on time. They will depend on a function lambda of t that essentially you can think of specifying, for example, an experimental protocol that the external agent wants to implement. And at this point, we can introduce a time reversal operation, which essentially swaps the initial and final time and makes time go backward. So this is what it looks like. And here we use the fact that the states themselves are invariant under time reversal. So the only thing that changes is the direction of time, not the state themselves. And we define it similar for the protocol. So also the protocol is inverted from the final state going towards the initial state as represented in these arrows. So now what we have to do is compare the probability of a certain trajectory with the probability of its time reverse counterpart, which is the trajectory that visits the states in reverse time with a backward protocol, with a protocol that starts with the final from the final state and goes towards the initial state. Good, let's do this calculation. So again, the path probability is what we have seen before. And when we compute this ratio, something that is useful is that the backward trajectory will spend the same amount of time in the dwells with the same value of the rates. So there will be in the denominator terms, these exponential terms, identical exponential terms corresponding to dwells as in the numerator. So these terms will immediately cancel out. That already simplifies quite a lot our situation. So what remains is the probability of the initial state in the numerator, which is our starting point for the forward trajectory, the probability of the final state at the final time in the denominator, which is the starting point for the backward trajectory. And then you will have the ratio of forward and backward rates every time a transition occurs. And this is because if, say, the forward trajectory makes a jump from x0 to x1, then the backward trajectory makes the opposite jump at that time. Okay, so this is already slightly more compact than what we had at the beginning. So now we can bring some physics into the game and think that we want this master equation to represent our physical system that we described in the first part of the tutorial. And so we can rewrite this ratio of rates using the generalized detail balance condition. So this ratio of rates will be equal to the heat exchanged during this transition. And therefore, this product will be simply equal to the exponential of the total heat produced during the trajectory divided kBt. This is directly the generalized detail balance condition. The other thing I will do is write this probability as the exponential of the logarithm of the probability, so that I have everything at the exponent. And you can see that now if I take this expression and multiply and divide by kb, I will obtain at the exponent precisely the total entropy production. So all these very lengthy and tedious expression involving this path probability, in the end, we reduced it to the exponential of the entropy production divided kb. We can rewrite this expression in an even more suggestive form and say that the entropy production rate is equal to kb times the logarithm of the probability of the trajectory, the path probability of the trajectory, divided the probability of the same trajectory in the reverse protocol. So this expression that I consider one of the nicest results of stochastic thermodynamics is the connection, is this direct connection between entropy production and the statistical asymmetry between forward and backward time that I anticipated at the beginning of this part of the tutorial. So as I was mentioning, this relation is not only very elegant, but it can bring us to this integral fluctuation relation in a very simple way. So the first relation we'll discuss is the so-called integral fluctuation relation. This relation states that the average of e to the minus entropy production over kb is always equal to 1 for all for all processes. And the way we can prove it now is very straightforward, because we can write explicitly this average as a sum over all possible trajectory, and we express the entropy production using this irreversibility relation. And you can see now that if I simplify the exponential with the logarithm, I'm left with the integral of all the trajectory weighted with the probability of the reverse protocol, and this is equal to 1 because the path probability is normalized. So this is a very straightforward demonstration of the integral fluctuation relation once we have this irreversibility condition. So the integral fluctuation relation is a very important relation. It has a number of main consequences. So the first is that we can get the second law, the average second law. So the fact that on average S dot must be non-negative. We already knew that from the Schnackenberg formula, but it's nice to derive it from the integral fluctuation relation. And in this case, if we take the logarithm of this expression, we get that the logarithm of this average must be equal to 0. And then we can use Jensen inequality because this is a complex function. And therefore, we directly obtain that the average of S dot must be positive. The second thing, which is a bit less trivial, and we didn't derive it before, is that the integral fluctuation relation implies that there must be a finite probability that S dot is negative. So it's possible that you observe a trajectory that apparently violates the second law of thermodynamics. Or in other words, the second law of thermodynamics is valid on average in stochastic thermodynamics, but not at the level of individual trajectory. And the reason to see that is that imagine you can prove it by contradiction. Imagine that it was not true. Then if this is not true, then this average would have support, the integral implied by this average would have support only for positive values of S dot. But in this region, the function that I'm averaging is less than 1. So there's no way that this average can be equal to 1 if S dot has support only for positive values. So the other way you can see it is that for positive value of S dot, this quantity is less than 1. For negative value of S dot, this quantity is larger than 1. And therefore, if you want these two things to balance to give us a total average 1, there must be a finite probability that S dot is negative. So this is a quite important and non-trivial consequence of the integral fluctuation relation. At this point, I think it's nice to discuss the Jarzynski inequality, which is one of the most celebrated results in stochastic thermodynamics. And in this perspective, the Jarzynski inequality is a way of seeing what happens in the context of fluctuation relations if we have a transformation that starts and ends at thermodynamic equilibrium. So these two equilibrium states do not need to be the same. The average energy, for example, might be different because of the action of the protocol, but the starting point and the end point are equilibrium state. So if this is the case, for example, the probability of the initial state is the Maxwell-Boltzmann distribution by assumption. And therefore, if I compute the stochastic entropy, I have to take the logarithm of this quantity, and I can write it in this form. And I'm using the fact that KB log of Px minus KB log of Px is equal to the free energy. And I can make the same consideration for the final time. So if I substitute this expression in the expression for the entropy production, I obtain that the entropy production is equal to e to the minus q plus the energy difference between the initial and the final state minus the free energy difference between the initial and the final state, which is also equal to minus the work using the first law of stochastic thermodynamics minus the free energy difference. And now I can use the fact that the free energy is a deterministic quantity, it's an average quantity, it's an ensemble quantity, and it doesn't fluctuate. And therefore, I can bring the free energy term to the right side. I can bring it outside this average. And I finally obtain classic form of the Jarzynski equality, which is this expression in the box. We will comment a bit more about the importance of the Jarzynski equality at the end. So at this point, I would like to spend. I will discuss another small technical point about time reversal and irreversibility, and in particular, if we look at this expression that we derived, so we saw that the entropy production is proportional to this ratio of probability, and now we can ask what is the entropy production of the reverse trajectory. So if you look at this expression, this might suggest that the entropy production of the reverse trajectory is simply minus the entropy production of the forward trajectory, because if I swap the reverse trajectory with the forward trajectory, the logarithm changes sign. However, here there is a technicality. So here, when we define the reverse trajectory, we have in mind a trajectory that starts with the distribution that the system has at the final state and is evolved backward towards the initial state. So if you do this transformation at the level of the probability distribution, there is no guarantee that you will end up in the equilibrium state, in the initial state of the forward trajectory. So if that doesn't happen, then this thing is not necessarily true, because for the entropy production of the backward trajectory, I should go back to this point and evolve forward or backward for the backward, sorry for the play of words, from this point, not from this point. So if we have a situation where the evolution of the backward trajectory ends up in the initial point of the forward, initial distribution of the forward process, then we say that the involution property holds, which means that the entropy production of the reverse process is minus the entropy production of the forward process. There are at least two important cases where involution holds, where this is the case. One is where the system is evolving at a steady state, because the distribution over the system state is constant in that case. And the other case is where this protocol starts and ends at equilibrium, because the equilibrium state is the equilibrium state. It cannot be a different equilibrium state. And therefore, you will then end up, when you go back, to the same equilibrium state. Okay, so if this additional requirement holds, then we introduce it because this is permits us to derive a stronger version of the integral fluctuation relation, which is the detailed fluctuation relation. And in particular, here we have to see what happens if we compute the average of a certain function of the entropy production times the exponential of minus entropy production over kb. This is the same fact that we had in the integral fluctuation relation. So we can do the same trick as for the integral fluctuation theorem. We use the irreversibility condition, and we transform this as an average over the backward process. And now we use this hypothesis that entropy production is an involution, and then this becomes an average of the function calculated for minus the entropy of the backward process. So this is, again, it's a general relation. And now if we take this function as a delta function of a particular value of the entropy production, the integral goes away because we are introducing a delta function, and we obtain this condition, which is the detailed fluctuation relation. So this condition is telling us that the probability, the ratio of the probability of observing a certain value of the entropy production divided the probability of observing minus that value given the reverse protocol, so manipulating the system in the inverse way, must be equal to the exponential of the entropy production. So this relation is important because it tells us that, again, under this additional condition, the distribution of entropy production satisfies pretty strong constraints. In particular, if I know the distribution of entropy production for positive values, then there's no, there are no degrees of freedom for the negative values, because I can compute all the probability of any negative values given the positive values using this relation. So essentially, half of the distribution is sufficient to compute the other half for any system. And here now we can do the same reasoning that we did for the Jarzynski relation. Take the integral fluctuation theorem. We saw that this theorem holds if the initial and final state are equilibrium states. And we can use again that in this case, we also know that the entropy production rate can be written as the work minus the free energy over the temperature. This is again the same argument we made a few slides ago. And in this case, we obtain the so-called Crookes relation, which is a similar relation, but for the distribution of work. So it states that the distribution of a certain value of work divided minus the same value is related by this expression. Okay, so now I just want to conclude by telling a bit more about Jarzynski and Crookes relations, and in particular why they are important. And let's focus, I mean, this is true for both of them, but let's focus on the Jarzynski relation for simplicity. So you can see that on the right-hand side, you have an equilibrium property, which is the free energy difference between two given equilibrium state of a certain thermodynamic system. So this is the kind of thing you would study in classical thermodynamics. So you have a system that undergoes a certain transformation between two equilibrium states, and there will be a free energy difference between these two states. And on the left-hand side, you have a non-equilibrium property. So you have an average of the work over an arbitrary protocol. So the non-trivial point here is that you can relate an equilibrium property with a non-equilibrium property computed over an arbitrary transformation. So this is a quite surprising fact. And this is also quite useful for experiments because in some cases there are small chemical systems that are hard to manipulate adiabatically. So if I want to measure, for example, a free energy difference between two configurations, it is hard to do it by performing this transformations law as one would do in conventional thermodynamics. And these kind of relations permit us to do these measurements using a non-equilibrium protocol instead of an equilibrium one. So I conclude here. I would like to thank my group members. These are my people in my group at OIST and my funding sources. And thanks for your attention. I'll be happy to take more questions.